Thank you very much, Lady Chairperson. It's really a great pleasure to be here this day and to take part in this event. And of course, it's always a pleasure to come to St. Petersburg. It should be a short way from us. It was a little bit more comfort for me this time. I will be speaking today about a little bit broader topic than the one proposed in the program, because I think it's of general interest also to get an insight into the mechanisms of salt gel process for metal oxide particles. So of course I will be speaking, especially at the end, about specific features of interaction between metal oxide nanoparticles produced by salt gel method and protein molecules. But I will take some more examples on the way there, and also will speak about how the metal oxide particles are emerging and how they are actually destroyed sometimes by molecules. And in my presentation I will start with a very short introduction to general principles of the salt gel process. I will also briefly speak about natural nanomaterials and how they emerge, because my colleague Graham Seysenbayeva in the afternoon will take a deeper insight into this part. And then I will be speaking about what metal oxide nanoparticles are doing and can be used for doing in nature, how they can be mediators of bacterial interactions and nanozymes. Nanozymes is nanoparticles which act as enzymes in biological processes. And also about mineral nanoparticles in modulating immune response. I will show some few interesting results which we have obtained during the last 2 years. And also we'll put some attention onto interactions of metal oxide nanoparticles with blood. And in this part we have collaborated a lot with ITMO University here, and I will give credit, of course, to people who helped us. And also we have started to get fundamental insights into the chemistry of protein corona of metal oxide nanoparticles. We have looked on very simple models how the interaction takes place and what are the interesting features there. And finally some conclusions and future perspectives. So when we're speaking about salt gel of metal oxides actually, these are salts of metal cations and oxide anions. So the chemistry there, in principle, it is the regular solution inorganic chemistry, which is based on nucleation and the processes which are following the nucleation. It can be either growth or aggregation. And if we get particles which are nucleation size, it's 3 to 5 nanometers, actually what is happening, we're getting a salt which can be very stable, and then when they find each other and build a three-dimensional structure, this is a salt gel transition. So salt gel, of course we are here in the walls of the Institute of Silicates, but it's not only the prerogative of silicates, because salt gel can be made with sodium chloride, calcium carbonate, for example, getting transparent salts and transparent gels, and also transparent proteins. So if we stay at the step of nucleation size, 3 to 5 nanometers, keep particles from growth especially, so there should be very low solubility of the material in the solvent, then we'll get this colloid solution, salt, which will be possible to transfer into a gel. How does the nucleation occur? In this case, because we work with metal oxides, actually we can say with salts, there are two principal mechanisms. The simplest salts, like halides, usually it is considered that they nucleate through dense droplet model. There is a supersaturated solution containing cations and anions. They are in a little bit increased concentration. They find each other and form another crystal. And then usually well-soluble inorganic salts, they grow very quickly. So with sodium chloride, for example, it's very difficult to get into the salt gel process, but it is possible. With metal oxides, because they have very low solubility, even in water and even less in organic solvents, what is usually happening, it is a process of nucleation through coordination mechanism. There are individual species which are formed actually in coordination equilibrium, and I will try to show you how this equilibrium is manifested. So for silica, there is a possibility to speak about hydrolysis and condensation kinetics on the way to the silica particles. For metal oxides, this is not relevant because it's an equilibrium process. If you add distinct concentrations and ratios of ligands, of metal cations, and solvent, you will get very distinct species. So, why is it in this way? Well, first and foremost, for metal oxides, the reactions of hydrolysis and condensation are reversible. They are reversible for all of them, and we have worked with molecular chemistry. We have seen examples of, for example, preparation of metal alkoxides. Here you see alkoxide bridges from hydrated salts. But of course, it's necessary to have alcohol as solvent, and also it's necessary to have some ligands to thermodynamically stabilize the alkoxide species. But of course, it is possible to use these species for salt gel in, for example, basic medium, and produce aluminium or gallium indium oxide from aqueous solution of these species. So surely this process is fully reversible. What is also very important, it is that for metal oxides there is no memory between different steps of this equilibrium. The structures which are produced, they are not kinetically controlled, they are not as organic molecules where some group is replaced. In this case, there is a total regroupment of cations and anions, and in each case, what we see is a result of dense packing of cations and anions. So when we start from a real alkoxide, where only alkoxide and different ligands here, nickel, titanium, the ratio between cations is 1:1, it's nickel 2, titanium 2. You add one equivalent of water to it. What is crystallized from it quantitatively, it is a compound with a cation ratio 5:1, and containing also one oxyligand which is introduced by this water molecule. What is also very important to remember, and I know that Ulrich Schubert is a little bit like famous Swedish chemist Carl Scheele, who has discovered oxygen. If you remember the phlogiston theory, so Carl Scheele remained an adept of phlogiston theory until his death, but he was the first to discover and to isolate pure oxygen gas. So Ulrich Schubert, he was usually postulating, you can see in several reviews, that these chelating ligands, they are decreasing the kinetics of hydrolysis and condensation, and his idea was also that they are sitting still on metal cations. This is simply not true. They're very quickly moving, and kinetically they are increasing their reactivity. The effect of chelating ligands is that they simply are stabilizing the species which are formed, this nuclei, this metal oxide nanoparticles in solution. So what we can conclude is that everything, what is happening on the way from individual metal organic precursors into primary particles in salt gel, of course it is hydrolysis, polykondensation, but it is leading to core structures which are densely packed of cations and anions, and in the core they can be crystalline. I will show you an example when these particles already are crystalline. You can see the X-ray diffraction from them. And they are covered by residual organic lipids. And what is also very interesting, of course, they resemble polyoxymetalates, which are formed in aqueous solutions for metal hydrolysis. When hydrolysis of metal cations is occurring in aqueous solutions, in some cases they're very thermodynamically stable species, we can see them. There is another extreme. Now people, especially in China and some Chinese colleagues in the USA, they are very much prone to study what they call alkoxide clusters. And what they think, because they can see same kind of structure in some intermediates, oxide intermediates, polyoxymetalates, somehow they conclude that this should be clusters. And clusters are very different things than these polyoxymetalate structures we get as intermediates in salt gel. Because clusters, what Albert Cotton has, for example, studied, these are structures which are very stable. So they are so stable in solution that you can cook some, for example, molybdenum sulfide clusters in concentrated nitric acid, and you only will replace some outer ligands, given number of them. Of course, oxo-metallized constructions which are formed in the salt channel hydrolysis of metal organic precursors, they're absolutely not like this. These are products of equilibrium at given ratio between alkoxide ligand and chelating ligand and water. If content of water is changed, these structures will change. And of course, in some cases, you are getting the same structure, for example, for normal propoxide and ethoxide ligand. But the reason is that the size of this ligand in packing is the same. Because if we take isopropoxide ligand, it will be the same construction principle, but the structure will be absolutely different. So in this case, we have NFAs-like structures, triangles of octahedron, H sharing, and it is niobium 8. And in this case, with isopropoxide, it's niobium 6. So dependent on the size, there will be different kinds of packings. The principle is, of course, the same. If you go back to basic inorganic chemistry, it's, of course, all the rules that decide how it is compacted, how it's put together. But these, of course, are not clusters. It is interesting to study these structures because even if they are intermediates on the way, they are metal oxide cores. They resemble the surface of metal oxides, bigger particles. Normal particles, again, they have a size between 3 and 5 nanometers. Those ones, they are just below 1 nanometer. So these are, in a way, particles, but they are not stable in solution or in solid phase. If we add more water, for example. But still, they were interesting. So what we have done, we have looked how these particles are attaching to them, for example, medicines as ligands. In this case, it's triclosan. It's a very typical broad-spectrum antibiotic. And I will show you an example how we have prepared, for example, patches for treatment of skin diseases using triclosan attached to titanium dioxide nanoparticles. So from the point of view of how these ligands are attached to the core, it's absolutely okay to discuss these objects as nanoparticles and as individual objects. What is happening, unfortunately, for good or bad, it is that these colleagues in China and in US, they have started to speak about single molecule photochemistry. What they're doing, they're producing titanium oxide species like this, and then they add water or aqueous solution of sodium sulfate or something, and then they study the photochemical effect. And I will show you what is happening, but they believe that they just remove the oxide ligands here and put OH, and it remains as oxide cluster. So the word sometimes is very misleading, and it is the word is very much what we believe. First was the word. So in this case, I would like to quote, in this case in Russian, because it's an English translation here, a joke that my teacher of mathematics was saying very often. What he used to say just to cheer up the students, he was saying, давайте нарисуем отрезок, назовем его БК, возьмем БК за рога. We of course understand that a linear segment will never be an ox and will never have horns, but people who call things clusters, they honestly believe that they are clusters, and then they start doing things they should do with clusters and expect that the effects will be as from clusters. But they are not. So the problem is, here you see an AFM image. If we take these so-called clusters and add more water, what will happen? They will transform into these primary particles of salt gels. So from the size below 1 nanometer, they will immediately grow to above 3 nanometers and will have NFAs structure. And of course, in X-ray, you will not see in this case the pattern, but if you use other techniques which are sensitive to structure, X-ups, for example, or electron diffraction, you will see that it is NFAs. So, what can be done with this knowledge and understanding that metal oxide salt gel is proceeding through polyoxymetallic-like structures? Well, first and foremost, it's necessary to focus on distinct types of materials. Because we are at agricultural university, we are interested in biocompatible oxides in the first hand, and also biocompatible salts. And my colleague Renee in the afternoon will tell you some more details. But the matter is that weathering of minerals has, through all the history of Earth-produced nanoparticles all around, both in soil and in aqueous solutions, through just weathering of minerals. And what we do, we are trying to use in the first hand these kinds of materials. What we can also observe is that in some cases it's possible to envisage how the nanoparticles are formed in nature. In this case, we have looked at very easily shifted equilibrium of so-called T-bar. It's a very strange commercial name, but it is the one for this oxo complex. It's very cheap because it's a byproduct in production of titanium for paint. And if you take this product, which is small molecule, which is a clear, true solution, and add, for example, less polar solvent to it, like methanol or ethanol, there will be formation of spherical 3 nanometer size nanoparticles, very individual ones. You will be able to see X-ray diffraction pattern of anatase for it. But then if you add more polar solvent, water or dimethyl sulfoxide, they will retransform back from this complex and oxo particles into this oxometallate soluble species. Why is this interesting? Well, it means that it is possible to stabilize particles in solution using very simple biocompatible organic ligands. What we have patented, it was application of triethanolamine. It is possible to use a complex bearing this kind of ligands, to charge it by addition of acid in hydrolysis, and then particles which are stabilized by positive charge are produced, and then very stable. So this material, it's salt of primary particles. It is infinitely stable for years. You can dilute it by ethanol, by water, or by another alcohol, and it will remain transparent salt. So what is interesting with this, it is that titanium, of course, has huge affinity to different biomolecules. In the first hand, it has affinity to phospholipids in the cell membrane. And what is possible to do in this case, it is possible to encapsulate bacteria, for example, gram-positive bacteria, those that have phospholipids accessible, or teichoic acid, which is a phosphoric acid ester, in the cell membrane. And what is also possible, it is possible to combine this affinity to encapsulate bacteria first, and then to stick it to the roots of plants. And this causes the increased growth of bacteria, formation of biofilm on roots. And the result is, if we take biocontrol microorganisms, which are helping bacteria to fight against fungi, the result will be very nice. So the plants will be able to survive a fungi attack, in contrast to those non-protected, and even better than in the case of application of biocontrol bacteria directly onto the roots. What is also interesting is that metal oxide nanoparticles, in some cases, they have redox activity. And iron oxide nanoparticles, it is, again, they are called iron oxide nanoparticles. In some cases, they're called spiral superferromagnetic iron oxide nanoparticles. The matter is that it is a common name like for titanium, but there are lots of different compositional structures. In this case, we have studied iron oxide nanoparticles that were stabilized by yttrium in the McKimite phase. And what is possible in general for iron oxide, it's two kinds of activity. It is catalyze-like activity, what we know when, for example, we put hydrogen peroxide into blood. The blood is coagulating and oxygen is evaporating. And the other is peroxidase-like activity, formation of hydroxyl radicals. So this type of behavior, it's very good for plants. It will relieve them from stress, for example, drought stress, when there is too little water and plants start to produce reactive oxygen species. And this kind of activity is very dangerous because it will oxidize plants more and increase the stress. So when iron oxide is doped with yttrium, this McKimite structure is behaving like a catalyst. It is actually decreasing the content of hydrogen peroxide in the beams very distinctly, and more when it's high concentration of iron oxide particles. We have, of course, checked against pure iron salt. Iron salt actually is not taken up by the roots because they have protection mechanisms against it. And also we see that the concentration of oxidation products in the leaves is distinctly decreasing on increasing concentration of these kind of iron oxide particles. So the result is that bloods are distinctly feeling better when they are watered by solution of stabilized iron oxide. And this is visible both in leaf growth, in the size of leaves, and also in the concentration of chlorophyll. That value is an arbitrary, specific unit for chlorophyll concentration. So they're greener and they're bigger. They're feeling better when they're subjected to drought. What is also very interesting is, of course, that it is a challenge to encapsulate human cells because they are naked, they are covered by this phospholipid membrane, and for them it can be too huge stress when they're coated by a layer of titanium. But if combined with proteins, and that was one of the first motivations for us to start looking at protein interactions, when coated by a layer of titanium oxide and proteins, for example, the UCAT, the immune cells, they keep their capacity to respond to biological stress, for example, to feel the presence of charged immunoglobulin molecules, and release the interleukins, the chemical markers interaction showing that they are feeling the presence. They are protected when they are coated by this shell. They are more stable against temperature stress. For example, they can stay temperatures of 42 degrees. They are more stable to chemical stress if you want to poison them, but still they are feeding by molecules and giving normal response. What was also very interesting for us is to understand what is happening when oxide nanoparticles are meeting blood. Blood is a very complex system, and what we have learned, partly from nutrition, partly from our colleagues at ITMO, that the behavior of metal oxide nanoparticles can be quite different. In some cases, for example, iron oxides are absorbing proteins, and supposedly specifically, I will show you an example, but without chemical transformation, so they do not cut the molecules, they do not build new molecules. Aluminium oxide hydroxides initiate hydrolysis of peptide bond. There are some very nice papers from our colleague at ITMO. And titanium oxide generally was thought to cause enhanced blood clotting, and there were some preliminary results of our colleagues from medicine faculty at Uppsala University from Rudbeck Laboratory. So we have looked closer at this case, and of course size and shape of the particles also play a role, but I don't have time to look more closely on this. What we were able to see that there are, of course, some effects of size and shape. So if we have big particles, then it is a complement system which is activated. And complement system, it's like primary immune response in blood. It is recognition of allele body in the blood. So in this case, inflammation starts. When we have small particles which are not interacting with these big molecules, which easily change conformation, then it is so-called kallikrein kinase pathway. It is the biological pathway that regulates not inflammation but blood pressure and also feeling of pain. So in this case, it is this mechanism which is activated, and it is activated through specific interaction with some biomarkers in the blood. Because we were inspired by this idea that titanium oxide should clot the blood, should stop the blood flow, we have, together with our colleagues at ITMO, and the results are published in this paper, it's a scientific report, Nature Publishing Group, we have looked what is happening when we add dispersion into the blood, and what we could see, it's not in this image actually, it was very increased and enhanced clotting very quick. Clotting very quick formation of a hybrid material based on protein and titanium, which is solidifying the blood. And when rats were treated with titanium dispersion, what we could see, it was on one hand a very clear decrease in the size of the wound, so the wound was drawn together. And this feature actually is general for any colloid, so whatever you add, there will be some kind of this effect. But what we also could see was that there was distinctly improved healing. So in group 2, it is second-degree burn after treatment with titanium, and in contrast group 1 without treatment, and group 3 it is without treatment, and group 4 it's fourth degree burn like group 3, but with treatment with titanium. What was very exciting, it was that the structure of skin which was regrowing was very different in the presence of titanium and without treatment with titanium. So what we could see here, for example, we have the regrowth of skin without treatment with titanium, and you see there is very little of speciation, formation of structure of the skin, because there are different kinds of cells. They are growing mostly as connective cells, while in case when the titanium treatment is applied, there is much more complex structure. The skin is reconstructing. And what we could see, even there is, in the case of second degree burn, practically no formation of scar tissue and practically no discoloration, which is very common for burning treatment. What is also very exciting is that there is no retention of titanium in the inner organs of the rats. So they are treated by titanium and the open wounds, but nothing statistically seen is transferred into the lungs or brain or liver or spleen, so they remain healthy after this treatment. What is also interesting to mention that, of course, we have produced also hybrid materials where the titanium is attached to nanocellulose to combine the positive features of two types of materials, because cellulose is very hydrophilic, so it's keeping water, humidity on the wound, and also helping in this way to regrow. But what we can do in case of addition of titanium, we can form complexes on the surface with molecules of medicines, and in this case, dependent on how we construct this outer surface, it is possible to control the release and achieve controlled release between hours and several days, up to 1 week, of antibiotics and painkillers, etc. So it looks as a very prospective direction. And finally, what was very interesting for us was to get some direct molecular insight. How can we see what proteins are doing with nanoparticles? So what we have done, we have used nanoparticles which are stable in aqueous solution. It's so-called phospholipid phosphatungstic acid, because these anions, they are considered to be true ions, but they have the size of 1.04 nanometer. So these are nanoparticles directly in the proper sense of this meaning. And what was interesting for us, it was to understand what are the chemical reasons why different oxides are behaving differently. If they have the same shape, the same size, more or less the same chemical properties, still there is a considerable difference. So if we take a spherical particle of iron oxide, a spherical particle of titanium, their interaction with blood, for example, with blood proteins, will be very different. So we decided to look at two very analogous types of nanoparticles, phospholipid and phosphatungstic acid, and try to co-crystallize them, make true crystals and determine X-ray structures with glycylglycine, very simple peptide. So the first thing we were able to observe was that there were different crystallographic phases forming dependent on the concentration of solution. So there was, we could see directly some complex chemistry there, but still we were seeing only these particles. But what we also were able to see that the interaction between peptide and anions particles was very different. Because in case of molybdenum, it was mostly electrostatic interaction. It was the positively charged ammonium group which was turned towards the anion. And in case of tungsten, the behavior was very different, because it was mostly hydrogen bonding between the protonated peptides themselves and also with the anions of phosphatungstate. And this really is a considerable difference. What we also were able to see was that the anions were not staying intact. It's very exciting, because people usually still are understanding, appreciating these anions as a final step. So as soon as, let's say, oxide particles are formed, they are not destroyed. There are some works on electrospray mass spectrometry for the formation of oxymetalates by Larry Cronin, where it was pointed out that it is possible to follow how the formation occurs from small molecular species into this, let's say, nanoparticles. But what we were able to see was that both for molybdate and for tungstate, in solution, we saw very complex equilibrium. So there was very little of impact, let's say, particles in the presence of this simple peptide in solution. Mostly sometime after the solution, because we followed also this process with NMR, so we saw that they were dissolving as particles and peptide, but with the time they were transforming into very complex mixtures. And this is the equilibrium mixtures after 24 hours. So what we can see here, we can see hexane, molybdate, and we can see beta tungstate, and you can see, of course, some remains of the original bigger particle. But not much. In the case of molybdenum, almost nothing. In the case of tungstate. So the interaction, it's not in one way. It's not only what particles are doing with biomolecules, it's very much also what biomolecules are doing with particles. And in many cases, biomolecules are capable to cut the particles into small molecular species, which can have quite different reactivity. And this we will be working further on with our colleagues at DITMO, because this is very exciting. But the matter is that the chemistry of metal oxide particles, it's very interesting, very exciting, and when they are small enough, it's all the time coordination equilibria, which are dependent on what is present in solution. And with this, I would like to conclude that, of course, this is a very exciting area. It is possible to find materials which are fully compatible with our bodies, and they have very, very exciting reactivity, and we have scratched on the surface, but we are absolutely determined to go much further in this. And in future, of course, we are looking for more fundamental insights, finding explanations of different reactivity. Here we already see some signs. And of course, developing design of future hybrid materials for agricultural and biomedical application. So I would like to thank the financial bodies that helped us, there were many, to all colleagues that helped us also, and to all of you for a kind attention. Thank you.
Обширный, интересный доклад, полный всяких концепций. Вопросы, пожалуйста. Пожалуйста.
Ну, я думаю, что будет слышно. У меня действительно очень интересный доклад, много впечатляющих результатов. У меня такой вопрос. Вы используете диоксид титана, и он оказывает ранозаживляющее действие, очень эффективно. Но ранозаживление, насколько я помню, что я раньше учил, это многостадийный процесс. Свои месяцы же есть. Так что получается, что диоксид титана воздействует на всех стадиях, то есть это универсальное как бы лекарство. Оно, вот у меня такой вопрос. Вы добавили, у вас рано заживление произошло быстрее, а на какой стадии действует? Возникает вопрос, потому что это же многостадийный процесс. Проходит один, месяц же запускает второй процесс, месяц же третий процесс. Так вот, где действует?
Well, I will answer in English. Of course, we have been looking at this, so we have confirmation in this paper for one step. It's the very first one of formation of the hybrid material. But what we have seen also from our works with iron oxide, and what we are studying now at the moment, it is this specific adsorption of proteins. Because there are mechanisms which are calling growth factors to this place. So titanium dioxide, it's not only creating film, it's also taking out or activating some biological mechanisms. What we could see on iron, it was this kallikrein mechanism. So it was binding to some kind of messengers which shifted the blood composition, leading at high concentrations to inflammation. Titanium dioxide is doing something different. So at the moment our colleagues at Rudbeck Laboratory are studying, in collaboration with my PhD student Frederick Svensson, what actually is happening. It's a very complicated process.
Конечно, сложно. Я говорю, что многостадийный механизм самом деле несколько методик.
Yes, and it seems that titanium dioxide has activity on several steps. Not only the first, not for everything. What people are most excited of it is to change the immune reaction, to maybe decrease the immune response to transplanted organs, etc. We are not yet there, and it will be very complicated. But with the regrowth of skin, we are close to understanding how things are going.
Но очень интересно. В любом случае, это очень интересно.
Thank you very much.
Спасибо. Скажите, пожалуйста, вот по поводу центральных планов, возможно, это как-то немножко связано. Известно, что сейчас развивается тоже направление, что не только химия поверхности влияет, но какие-то наноразмерные вещи на поверхности для антиматериальной активности. Вот не может ли это как-то быть связано, ваша работа, с определенными наноразмерными формами ваших частиц, форма, размер, для того, чтобы они называли какие-то антибактериальные эффекты, и тем самым способствовали очень заживлению рака.
Well, again, I would not say that this can be the case for our particles. They are too small because they are about 3 nanometers in size. So they do not have any specific size for creating a response. What you're speaking about, it is very interesting because implants usually nowadays it is considered that it is actually a good thing to oxidize them, the first hand, to make titanium oxide on the surface, to increase biochemical activity, to increase blood circulation on them and regrowth. But also the shape of surface, of course, plays a role, and what kind of holes and bumps on the surface are present is influencing what kind of cells will attach to those. And I know that my colleague Gulain was working with people in dentistry, with dental.
They make the size of the nanoparticle in this way that it's a good bacteria growing on the surface. So in this case, it's help to have healthy
So for that,
around this implant. But in the case of it, the size is too big, for example, and it's suitable for another bacteria, it will be another effect. So this is also sorry.
I will just say add to what Vadim said, that the size of particle and the holes around them playing the important role, because the size of, if the size is suitable for the good bacteria, it will be a good environment around the implant, and if it's not good size, and for example, size suitable for the bad bacteria, it will be inflammation. So this is important, of course.
but this size range is on submicro level. So bacteria, they're usually from, let's say, 100, 200 nanometers to microns. So this is roughness on this level.
Thank you.